Okay, so now we are going to be looking at spring force and energy here. So I have a brand new spring here, and you can see right now it has a natural length of all its own. There's nothing on here. When I add 50 newtons to it, we can see that the spring stretches 1 meter, and then when I add 100 newtons to this, it stretches a total distance of 2 meters. And so when we graph this, our graph is going to look something like this. Okay, where the slope, which is k, our spring constant, is going to equal something like 50 newtons per meter. Now, when we talk about energy, what we're going to see is that right now, at this very first one, there is no spring energy because there's nothing has been stretched. The spring doesn't contain any energy. When we have the 50 newtons pulling on the spring, we have some energy on here. And we can actually look at that and, oh, hold on, let me adjust this because my line was slightly off. There. Is that better? Yes, that looks a little better. Nope, I still had the same issue here. This is the point I want. Okay, that is the point I want there. Going straight up. Yep, to 2 meters. Okay, so yep, that looks right. So when I'm at 1 meter, you can see 50 newtons of force, and 2 meters is 100 newtons. Perfect. Okay, perfect. Now, what we can do, and what you'll notice here, is if we look at the graph here, we can see that there's going to be some spring energy. When this is stretched a little 1 meter, and then there's going to be more energy when we stretch the spring to 2 meters. Okay, and we can actually also see that based on the graph. So if we look here, what we'll find is this area. Remember, we have talked about graphs and how the area of graphs are very important and they mean things. This area is the energy stored in the spring when the spring is stretched 1 meter, or when 50 newtons of force has been applied to the spring. In fact, both of those are true, right? Whenever it's stretched 1 meter, it takes 50 newtons to do that. And you can see that if we look at this area, okay, this area is actually going to be much larger, and this is going to be the area, or I'm sorry, this is going to represent the amount of energy in the spring. When there is 100 newtons of force and it is stretched 2.0 meters. Okay, so in here, the area is going to equal our spring energy. Now, we're going to want to be able to quantify this or put numbers to this. And so we will do that. The area of these are triangles, so the area is going to be 1/2 base times the height. And our energy of the spring we're going to abbreviate as E spring. The base in this case is the stretch. So we're going to call that stretch. Whereas the height, that is the amount of spring force. So if I rearrange this and use my variables, we're going to get E for the spring is going to equal 1/2 of the force of the spring times the stretch. So let's go ahead and calculate how much force, or sorry, not how much force, how much energy is stored in the spring when it is stretched 1 meter. So using our equation here. So let's start with the 1 meter that was in blue. So we have 1/2. We know our spring constant is 50, not our spring constant, rather. The force of the spring, we said it was 50 newtons. And we know that we have been stretched 1 meter. So 1/2 of 50 is 25. And times 1 meter, which will give us 25 Newton times meters. Now, the unit Newton times a meter is good for energy, but we also have another name on another specific unit, which is the joule. So the energy in the spring when it is stretched 1 meter is going to be 25 joules. And we can actually see that if we were to go over here, we would actually be able to calculate that area from the graph. Okay, now we are also going to look at the energy stored in the spring when we stretch it to 2 full meters. So we'll bring that down here. Energy of the spring is equal to 1/2 force of the spring times displacement. We said it took 100 newtons to stretch the spring 2.0 meters. That leaves us 50 newtons times 2.0 meters, or 100 Newton meters, or 100 joules. So, stretching the spring twice as far with twice as much force ends up putting 4 times the amount of force, or sorry, 4 times the amount of energy. Twice as much force, twice the distance gives us 4 times the energy in the spring. And that actually makes sense if you look at these areas, right? This area here is going to be 1/4 of this bigger area. And we can actually make this into triangles and see 1, 2, 3, 4. So stretching it twice as far will give us 4 times the energy. Now, our equation for spring energy, we said, is 1/2 force of the spring times our displacement, or how much stretch or it's compressed. Now, this is all great and everything, but sometimes we're not going to actually know how much force and stretch happens. Okay, this is useful with data like we got in the lab, but sometimes we don't have that. Okay, sometimes we're not going to have force and displacement. So when that happens, we are going to use Hooke's law, which we just developed, and this together. So remember, Hooke's law said the force of a spring equals K times delta x. Now this is going to be helpful because K never changes. K is a constant of the spring. It's a property of the spring. It doesn't change. And so we can actually calculate the amount of spring energy using Hooke's law by replacing this with this. So instead of Fs, we're going to insert K times delta X. Now we still have delta X because that was originally in our equation. So we're going to combine those two, and we get a second equation here, energy of a spring, 1/2 K X squared. Now this is useful because sometimes we know about a spring constant, but we don't know how much force it takes to stretch that spring. And so this is a way to calculate and determine the amount of spring energy something has without knowing how much force it takes to do that. So that's what you guys are going to look at today. And the work that you guys, based on the work you guys had from last week and the spring lab. And next time, tomorrow, what we're going to be talking about is other ways to quantify energy and other energies. So we have spring energy here based on what we did in that virtual lab. And then we're going to look at other energies and other ways to bring in some of those energies that you guys know about and have learned about before. So that's all for today, and I'll talk to you guys next time. Have a great day.